So hi everyone. Thank you to be here connected to my PhD defense entitled Detection and Estimation of Stage Discharge Rating Shifts for Retrospective and Real-Time Streamflow Quantification. I have carried out my PhD at INRAE in the research unit of River Lyon in Lyon under the supervision of Michel Lang, Jérôme Lecoz, and Benjamin Renard. The thesis project was funded by EDF and CNR, both French national electric power producers, and CHAPI, the French hydrometry service, also tasked for flood forecasting and prevention. The overall purpose of this project is the quantification of river discharge or stream flow. In fact, the knowledge of the volume of water that passes through the river in a unit of time is important for retrospective purposes such as flood risk and zone mapping, or frequency analysis of floods or droughts, which is very important for the design of civil structures. Even more important is the quantification of stream flow in real time during high flows to forecast, prevent, and manage river floods, or to optimize the hydropower production, but also during low flows to ensure the ecological integrity of the river ecosystem, and also to ensure the continuity of human activities such as the cooling of nuclear reactors or irrigation. The overall, in other words, what we want to provide is the streamflow time series. There are several methods to measure streamflow. However, the bad news is that we cannot, in many natural rivers, streamflow cannot be measured in continuous. Instead, what we can measure in continuous is the water level or stage. The stage is usually measured at particular locations along the river, easily accessible, for example, nearby a bridge, and well equipped for data logging, the so-called hydrometric stations. So what we have is the time series of a stage. To obtain the stream flow time series, we need to establish a relation between stage and the discharge. This relation is commonly called the rating curve. And to calibrate this rating curve, we can use some occasional measurements of stage and discharge called gaugings. Notice that these gaugings are affected by measurement errors that must be accounted for during the rating curve estimation process. And the obtained rating curve is also affected by an important uncertainty that must be accounted for. So for each value of stage, we can compute the corresponding value of discharge through the rating curve. And we obtain the streamflow time series. The rating curve is commonly modeled by using a power law function, where the input variable is the stage, so the water level measured with respect to the zero of the instrument, and the output variable is streamflow, and parameters are A, B, C. The term H minus B indicates, in this schematic example, the water depth. That's the difference between the stage and the offset B. In this case, the offset B represents the riverbed elevation with respect to the zero of the instrument. The rating curve is not only affected by an important uncertainty coming from measurements errors, parameters uncertainty, and the perfection of the chosen model. More important for this thesis is that the rating curve can change over time and leading to stable hydrometric stations, which require a particular monitoring. The issue of rating changes has been broadly studied in the literature. Several authors make a distinction between two different families of rating changes, the transit changes and the sudden changes. The transit changes are represented by a progressive modification of the rating curve due to processes such as the growth or decline of aquatic vegetation, or by a backwater effect, due, for example, to sea tidal effect. Instead, in this thesis, we focused on the sudden changes or rating shifts, which are characterized by net shifts in the rating curve due to episodic events which occur in a very short time, such as intense floods or morphogenic floods, which cause riverbed morphological changes. As an example, we can consider the Ardèche River at Meyras in France, in South France. It is a gravel bed river that tends to degrade vertically after each intense flood. It has a classical configuration with a natural reef influencing the low flows, then a main channel influencing the medium flows, and a floodplain for the highest flows. At this station, the parameter the most affected by rating shift is the parameter B. It is the offset of the low flows. This B represents the riverbed elevation, or to be more precise, in this case represents the elevation of the natural reefal crest. On the stage record, we can notice that after the most intense floods, here indicated by stars, the stage record shows net shifts, vertical shifts. And these shifts are also clearly visible in the stage discharge plot, observing net translation to the left of the rating curve. From an operational point of view, there is a strong interest in detecting these shifts, both in retrospective and in real time. And it is also the main interest of this thesis. And several methods have been proposed in the literature, studying the discrepancies in the gaugings or changes, detecting changes in the low values of the stage record due to riverbed evolution, or considering arbitrarily discharge threshold. However, these methods have some important limitation. They are based in general on empirical rules, do not formally account for uncertainties of the input and output data, and in general, they cannot be applied in a real-time context. So this thesis work starts from these ideas and proposed in the literature and tries to overcome these three main limitations. Therefore, the main objective of this thesis is the development of tools for shift detection. In particular, we developed two tools for the detection of effective shifts. Thus, observed shifts for which the magnitude can also be estimated by using the gaugings and the stage record. And then we developed a third detection tool more suitable for the real-time application to detect the potential shifts or suspicion of shifts during floods based on sediment transport analysis. And finally, we wanted to develop a general protocol for the real-time application for the streamflow quantification, accounting for rating shifts. So the first proposed tool to detect effective shifts is based on the segmentation of the gaugings dataset. The literature proposes empirical rules to detect discrepancies when a new gauging departs for more than a predefined a threshold from the rating curve in terms of discharge or in terms of stage. And a more formal method has been proposed to analyze the temporal behavior of the residuals computed between the gaugings and a baseline rating curve. And in this case, the authors have applied classical Hubert segmentation to the time series of residuals and yielded for this station three homogeneous families of gaugings. The main limitation of this approach, and that we would like to overcome, is that it does not account for residuals uncertainty coming from both the measurements and the rating curve estimation. In this example, we show that neglecting this uncertainty, the data uncertainty, can lead to detect three segments. while accounting for this uncertainty may suggest that in fact only one segment may suffice. Another limitation is that the shift times are provided without uncertainty. And we believe that this uncertainty may be useful to search for the causing events. We developed an original segmentation method which provides shift times with associated uncertainties, recursively re-estimates the rating curve in order to refine the residuals and in order to detect some other minor shifts, and accounts for the residual uncertainties coming from both the gaugings and the rating curve. The method has been the object of an article submitted to Water Resource Research and now under minor revisions. The first step is the estimation of a baseline rating curve using the whole gaugings dataset. To this aim, several methods are available in the literature to estimate the rating curve with an associated quantitative uncertainty. And then we compute the residuals between the gauge discharge and the rating curve. And we, so as the difference. And we also estimate their uncertainty as the combination of the uncertainty coming from the measurements and the one coming from the rating curve estimate. So we obtain the time series of the residuals with associated uncertainties. Then we perform the segmentation of this time series through a Bayesian approach. The residuals are modeled as equal to the segment mean plus an error, epsilon, normally distributed with mean equal to 0 and standard deviation equal to the standard deviation of the residuals sigma e. The inferred parameters are the segment's mean, mu, so the segment's means, and the shift times, tau. The number of shift times is not known a priori. Thus, the segmentation is performed for an increasing, for a different number of shift times, and then a penalty criterion is used to select the optimal number. At the end of the inference, the shift times are provided with the most appropriate values, so here in blue, and the probability density, thus the credibility interval, for example, 95%. This interval can be further explored to search within the stage record for the event responsible for the shift, for instance, the largest flood, as in this example. And thus the shift time can be adjusted. Once we have detected the shift times, we obtain also the subperiods delimited by these shift times. So once the subperiods have been defined, the steps 1 to 4 that we've seen before are reapplied within the subperiods using the gaugings of the subperiod only. The rating curves are refined, so are the residuals, and it is therefore maybe possible to detect some other minor shifts. So at the first subperiod, no other shifts are detected. At the second subperiod, one minor shift is detected, and at the third subperiod, there's no shift. Then the second subperiod is subdivided in other two subperiods. And so the iterative procedure continues until no more shifts are detected within all subperiods. These are the results of the segmentation of gaugings applied to the Ardèche River at Meyras. And the results are encouraging with the detection of all major shifts and also some minor shifts. And this thanks to the iterative procedure that recursively reduced the uncertainty of the residuals. And results are in agreement with the official segmentation provided by the hydrometry service SPC Grand Delta. And as expected, the shift times are detected at the most intense floods and are provided with a useful uncertainty. In a stage-discharge plot, it seems that the method correctly disentangles the rating shifts from the gauging uncertainties. Then some other tests have been performed on on several other synthetic gauging datasets to evaluate the performance of the proposed method. But I rather prefer to show you the results on other two real case studies that have been processed, more challenging. And this is the Mat River at Escalier in Reunion Island, where the results show that the gaugings are mostly located at low flows, leading to very uncertain base rating curves and challenging segmentation. And the Wairau River at Burnet's Bank in New Zealand, which shows that shifts occur very frequently with respect to the gaugings. Thus, many periods have just few gaugings. The second tool that we propose to detect the fetish shifts is based on recession analysis of the stage record. The basic principle is that of this approach is that as discharge tends to zero, the water level, the stage, tends to riverbed B. In this case, tends to the elevation of the reef crest. Thus, what we can say is that the change in the low values of stage may correspond to change of riverbed elevation B. Some authors have proposed to analyze the variability of the annual minimum stage values and estimate the trends. You can see here the minimum values of stage for each year, and the trend analysis, which may correspond to the estimation of the evolution of the riverbed. However, this approach, the problem with this approach is that does not account for all available recession. It is based on an annual time step, thus not really applicable for to real-time purposes. And moreover, does not account for the uncertainty of the low flow values. So we propose a method which tries to overcome these limitations. And in particular, this method wants to analyze all available recessions, not only the ones that reach the minimum stage values. A method that uses a recession model where some parameters are in common to all recessions and other parameters are specific to its recession. And that this recession model should have one parameter corresponding to the riverbed elevation, which we want to estimate. This method is also the object of an article in preparation. The first step consists in the extraction from the stage record of all available recessions. The recession stage values are selected such as they are always smaller than the previous ones, and you can see here the black dots. Then one recession is separated from the next one when stage rises for more than a predefined threshold key. And we see here an example to the Mayra station with a key of 50 centimeters. And then we superpose all extracted recession together in the same plot, starting from the flood peak. The second step of the method consists in estimating all recessions extracted. First of all, we need to define the stage recession model to fit this recession data. We tested several models. I present here only the most promising one. It is a superposed exponential model composed of one exponential term represented the fast runoff after floods, plus a second exponential term represented the slower emptying of the aquifer, and third term, beta, represented the asymptotic water level, the asymptotic stage, which we believe correspond to the estimate of the riverbed elevation B. Parameters alpha represent initial stage values, while parameters lambda represent the recession rates. Then all recessions are estimated through a unique model, where some parameters are considered stable over time, thus in common with all recessions. Instead, some other parameters are recession specific. For example, for the model here, K indicates the recession index. So we have that lambda 1, lambda 2, and alpha 2 are assumed stable in common between all recessions. Instead, the initial stage alpha 1 and the asymptotic stage beta are recession specific. Beta is in fact the most interesting parameter to us, because a change of it may represent change of riverbed elevation. These parameters are estimated through a Bayesian estimation approach, which also provides an important information on the parameters uncertainty, and in particular of parameter beta. Thus, the first step is to analyze this parameter beta, in particular the temporal behavior of this parameter. And we apply the same segmentation method that we have proposed for the gaugings, because of its ability to deal with uncertain data. And these are the results of the segmentation applied to the Schrivet mirrors. We observe a slight variability of the parameter beta around the mean, the segment means, but the segmentation identifies anyway some major shifts and also some minor shifts. It is important to evidence that this method proposes, in addition to the rating shift times, also an estimate of the shift magnitude, whose means are computed from these segmentation results as the difference between the segments means. The segmentation can also be compared with the results of segmentation of gaugings. So we observe similar consistent results, even though the gaugings seem to be more accurate than the recession analysis. Is this method suitable for the real-time application? So to answer this, we need to carry out several tests. However, we believe that the proposed stage recession analysis may be of interest to detect and estimate rating shifts right after a flood and before a new gauging campaign is performed. So here you see an incoming recession compared with the previous past complete recession in red. We see that so after 5 days, the recession estimation is possible. And however, its uncertainty, we are just after right after the flood, thus the uncertainty is quite large. But then with time it refines, and we can see that already after 1 month, we may be able to detect and estimate a rating shift. Then we propose another tool as an indicator for fast detection of potential shifts during floods, using the only information available in real time, the stage record. This tool is based on some principles coming from the sediment transport theory. So intense floods may cause intense sediment transport, which in turn cause processes of erosion or deposition of the riverbed. Thus, the idea is that the longer is the flood event, the larger is the volume of transported sediment, Thus, the larger is the probability to have morphological riverbed changes. We also know that a minimum water depth, so in this case, a minimum stage, HC, is necessary to trigger bed load. We need to estimate this critical stage, which is not constant over time, because as riverbed evolves during floods, also this critical stage evolves. This analysis is, for instance, addressed to gravel bed rivers only. And the main problem that we want to solve is that we do not have sediment transport measurements. Thus, we cannot perform a calibration of the used models in a classical way. So let's see how we propose to calibrate it. The idea is that rating shift is detected if the stage exceeds critical stage HC, and we know approximate values for all parameters of HC, except for diameter D and the longitudinal slope S0, that are strongly site-specific, and if no field investigation is performed, their ratio, that we call phi, can have quite large uncertainty. Thus, to calibrate phi, we propose this. First, to identify some reference past morphogenic floods. For instance, we can use the results of the segmentation of the gauges and of the recession analysis that we have seen before, here represented with the red segments and the peaks of the floods with circles. And then we calibrate phi such that all flood peaks of the reference times are above the critical stage HC. So if we apply phi equal to 30, the last reference time, we see that the last reference time is missed, is below HC. Here, the segments in blue represent all events that exceed the critical stage HC. That's the potential shift times. So we need to decrease phi, for example, phi equal to 10. But so now we detect all reference shift times. But we see that we over-detect several minor floods. So we believe that choosing a middle value, like phi equal to 20, would be acceptable, for example. It represents a good compromise between detecting all reference shift times and avoiding the over-detection. Then the second objective of this method is to establish a relation between the volume of transported sediments and the corresponding rating shifts delta B to be used later in the real-time application. To this aim, we need the data of sediment volume and corresponding shift magnitude. To compute the cumulative bedload volume for each reference morphogenic event, we applied a bedload model very well known from the literature to estimate the flux. And then we multiply the flux by the time step delta T and the channel active with B. And we compute the cumulative volume from the beginning of the event. Then to estimate the rating shift delta B for the reference events, we estimate the rating curve for each period delimited by the reference flood events, and we estimate a parameter B for each period. Then the difference between the B of two successive periods represent the rating shift delta B. Then the principle behind the relation delta B and volume of sediments are that we don't have many data. You can see here. We don't know the nature of this relation. Thus, it's challenging to identify a proper model to fit this data. Then we want maybe the mean of the shift equal to 0, because what we want to estimate is its uncertainty rather than its precise value. And then we know that the larger is the volume, transported solid sediments during the flood, the larger is the uncertainty of the potential shift. Therefore, to fit this data, we propose this probabilistic assumption. The shift follows a Gaussian distribution with mean equal to 0 and a standard deviation increasing with the volume V. This relation will be very useful in real time to provide an uncertainty of the potential shift during the floods. The final objective of this thesis work is the design of a general protocol for the real-time application of the aforementioned tools. The necessity of solving the real-time issue is mentioned by some authors. However, they do not propose any general protocol. First of all, it's important to draw a clear distinction between the real-time and the retrospective analysis. In fact, in retrospective analysis, we have the study of the past hydrometric data, gaugings, and the stage record, which are fully available. On the contrary, in real time, we have the analysis of any data or information that is available in real time only. The retrospective analysis is still very important before starting a real-time application to calibrate the tools for the shift detection that then are used in the real-time application, and also to estimate the base rating curve of, at the initial time of the real-time application. Then, in real time, when a suspicion of a shift is detected, for example, during a morphogenic flood, also the validity of the base rating curve is questioned. And we enter, in fact, in a provisional period. And we provide the provisional rating curve, which may have much larger uncertainty than before. And then during the recession period, the recession analysis can be used to reduce this uncertainty until a new gauging is performed. And at this moment, the provisional period ends and a new base rating curve is provided. We propose a general protocol for the real-time application, which starts with the retrospective analysis, then proceeds with the real-time application, where the time step is adapted to the frequency of the incoming stage, for example, every 15 minutes. And then the application proceeds by investigating the rating curve stability at time t, making use of all available tools for rating shift detection and estimation. And if a shift is detected and a new provisional rating curve is performed, and the rating curve is used to compute the discharge, which is the main output of each time iteration. Finally, the provisional rating curve becomes a new base rating curve only if there are new gaugings. And in this case, so if there are new gaugings, a new retrospective analysis is performed. A new stable period begins. Otherwise, the provisional period proceeds in this iteration. The proposed protocol and algorithm implemented is in fact much more complex than this, but I rather prefer to show you a little demo on a known morphogenic event on the Ardèche River at Meiras. So these are the results of the retrospective analysis on this case study, and the study. So it is the study of the on the period preceding the initialization time, and then this figure now will illustrate a few crucial iterations of the real-time application. So on the left, we have the discharge time series with uncertainty, and the stage record below, preceding the initial time, and also the critical stage HC in green. Then in the middle, we have the current base rating curve with uncertainty valid at the initial time. And on the right, we have the shift detection toolbox, where the results of the three tools proposed in this thesis for rating shift detection are presented. The traffic lights indicate when a tool is on standby, so it is green. When a tool is activated but no shifts are detected, so it turns in yellow. And when a shift is detected, will turn on red. So in particular, the proposed application makes use of the segmentation of gaugings residuals on the top, and then the sediment transport analysis in the middle, and the stage recession analysis at the bottom. So this is the initial condition. Then nothing changed, nothing happens. And when then a minimum recession time is reached, the stage recession analysis can be performed, and the certainty of the recession curve is here represented in green. The segmentation of this time series of the current and past estimates of parameter beta does not detect any shifts, mainly because of the large uncertainty of the recession estimation. So the light is turned on yellow. Then a new gauging is performed, thus it is added to the gauging dataset, and the segmentation of the residuals does not detect any shift, so it's kept, the tool is kept on yellow. Then the third iteration, the flood begins, so the stage is well above, is not well above, is slightly above the critical stage for sediment motion. Hence, a potential shift is detected, and the tool of sediment transport is turned on red, and a provisional period begins. The relation delta B volume of sediments established in retrospective is used to estimate the uncertainty of the rating shift. But now we are just at the beginning of the flood, thus the potential shift is very small. Then at the flood peak, now the stage is much larger than HC, and also the volume of transported, the cumulative volume of transported sediments is much larger than before, and we can see we have larger uncertainty of the rating shift, and consequently also the provisional rating curve is now very uncertain. After 5 days, after some few weeks from the peak, the stage recession analysis can be performed. And the recession does not detect any rating shift, but it does detect, provide a valuable uncertainty on it, which is inferior to the one obtained through the sediment transport analysis. Thus, the certainty on the rating curve can be refined. And finally, a new gauging is performed. So it is added to the gauging dataset, and the segmentation of the residuals detects a shift, which so it is confirmed. So the light is turned on red, and the provisional period is ended, and the new base rating curve can be estimated using the new gauging only. So we can say that this application yielded promising results to this demo, and tries to account for uncertainty at each phase. However, before being validating the real-time application, we need several other tests on different flow conditions. In conclusion, in this thesis work, we have developed 3 original tools for the detection and estimation of rating shifts: a tool based on the gauging, one based on stage recession analysis, and one based on sediment transport proxy analysis. All 3 methods yielded encouraging results through the Dash River at Miraz, with the detection of all net shifts, but also some of minor shifts. And some other case studies have been proposed and studied and show preliminary good results. These tools try to deal with uncertainty sources at almost all steps. And they are also implemented into an original real-time framework, which shows encouraging results on one flood event. And the protocol has been designed to be flexible, allowing space for further improvement. And first of all, other more challenging stations must be tested before validating the methods. Stations with different bed composition, gravel bed or sand beds, We focus in this thesis on gravel bed rivers, but we believe that its application to sand bed rivers may be more challenging. And then also station with different frequency and intensity of shifts, but also different availability of the hydrometric data. And then a station with more complex controls, such as twin gauge stations, or shift or with shifts which may affect other rating curve parameters, such as the river width or the longitudinal slope of the roughness. To this aim, we have ongoing collaboration with CNR, EDF, and CHAPI to test some of their stations. And we also have some data from other organizations, and I want to thank. Then other sources of information may be used in particular for real-time purposes and can be implemented in the proposed real-time framework, such as measurements of surface velocity from radar can be measured in continuous, thus could represent a valid substitute for the sediment transport analysis that we have proposed in this thesis. The residuals of the stage velocity relation can be studied in continuous. Or we can study the correlation with a stable time series. For example, studying the neighboring stations. For example, analyzing a downstream frequently gauged station. Or the output of a rainfall runoff model. Then the proposed segmentation procedure could probably be extended to other fields where the relation between two observed variables with uncertain data is subject to sudden changes. As an example, the relation turbidity against the total suspended sediment concentration. And more generally, the proposed method could be used for segmenting a certain time series and can be applied, for example, to the time series of the annual maximum discharge. And finally, the implementation into operational applications is very important. First of all, we will need to implement a pre-treatment or visual checking of all input data necessary in order to detect anomalies or errors. Then, regarding the computational costs, the application in real time is performed within 5 minutes for each time iteration, thus within the typical time step of the stage records, that is nearly 15 minutes. And this makes the method applicable operationally. And also, graphical interface can certainly be improved. Another possible use of the proposed methods is to provide reliable calibration data for the real-time flood forecasting systems or to monitor low flows, but also this work would be of interest to better understanding the river morphodynamics. I conclude saying that the final goal is to help improving and optimizing the future strategies for gauging campaigns, which remain the most important instrument for streamflow quantification. I want to thank the members of the jury for their interest to this thesis. And then the members of the free thesis committee during these 3 years who provided important operational perspective. And finally, also some other hydrometric data suppliers from different organizations. So thanks for your attention.